ethanol or ethyl alcohol, probably one of the most famous molecules in history. Structurally, ethanol is a two-carbon chain with a terminal hydroxyl group, making it both polar and capable of hydrogen bonding. Ethanol is a common component in gasoline and biofuel, an antiseptic and disinfectant, and the active compound in alcoholic beverages. Alcohol dehydrogenase metabolizes ethyl alcohol into acetaldehyde using NAD+ as a cofactor. This process basically gets you hungover. If you want to see with more detail this particular mechanism, please watch this video. Also, ethanol is employed on the synthesis of diethyl ether, ethylene gas by dehydration, and oxidation into acetaldehyde or acetic acid, just for mention some examples. Ethanol is commonly encountered as a 96% solution. That's because as the temperature rises in a mixture of ethanol and water, a minimum boiling azeotrope forms. An azeotrope is a liquid mixture of two or more substances that boils at the same temperature, behaving as an individual substance. In this case, the azeotrope contains 95.6% of ethanol in mass, making it almost impossible to get 100% ethanol by distillation. Why will we need 100% ethanol anyway? Well, there are some processes that need as less water as possible, such as Fischer esterifications, where water reduces the yield, or in the formation of sodium ethoxide. There are dozens of methods to get anhydrous ethanol. In the next videos, we are going to explore some of them. Today, I'm going to use 3 Angstrom molecular sieves to get 100% ethanol. To start the experiments, I took approximately 600 ml of some forgotten 96% ethanol from a previous run. Then I started the addition of 3A molecular sieves, which can be purchased in a lot of different places. They are very messy and very difficult to add actually, so I decided to add them with a spoon. Just for be sure, I previously dried the molecular sieves at 250 Celsius for 2 hours. Molecular sieves can remove up to 22 grams of water per 100 grams of molecular sieves. So in my case, I added approximately 200 grams, which is more or less the double I needed. These tiny bubbles you see are the sign that molecular sieves are doing their job. I let the ethanol to rest for one night, and in the next morning I measure up the concentration using this alcoholometer, which basically correlates density with alcohol concentration. As you can see, the ethanol is at the 100 mark, so basically molecular sieves did a great job removing water. The next step is to filter the solution to remove any suspended particle, but this is optional, you can just simply decant it off. The particles made their way through anyway. Then I set up a fractional distillation apparatus. I discarded the first 50 ml of distillate, although its concentration was approximately 100. I measured the concentration of every 100 ml distilled, and they all result to be 100%. I continued the distillation till there was left 30 ml approximately. As a final test, I measured the concentration of all the distillates combined, and it results to be 100%. For storage, I added approximately 30 grams of molecular sieves for preventing the ethanol to get moisture. At the end I got 400 ml of anhydrous ethanol, which means that I lost 200 ml in the process. That is crazy actually. In this small bottle are the 50 ml of discarded ethanol, which I will be using for washing or things like that. In this table I listed the most important advantages and disadvantages on using molecular sieves for drying. So that's it for today. Thank you for watching, please subscribe and keep tuned for the next videos.